In this video, we're going to derive the moment generating function for a Rademacher random variable. Now, first of all, this probability distribution is not that commonly known, so I'm going to quickly make a point of what it actually is, but it's very simple. So all it is that if x is a random variable and it has a Rademacher distribution, the parameter is almost always 1/2, okay? And that means that the probability that x takes the value 1 is a half, and the probability that it takes the value -1 is a half as well. So it's kind of a bit like the Bernoulli distribution, except it doesn't take the values 1 and 0, it takes the values 1 and -1, and it's kind of a specific case because p is just a half. Now, technically, there's no reason why it has to be a half, but this is just what it's commonly is. So you technically could have a Rademacher distribution with a parameter of p, where the probability that x takes the value 1 is p, and the probability it takes the value -1 is 1 minus p. But we're going to do it for 1/2 because this is the most common thing, and this is kind of definitionally what it is. So let's actually get the moment generating function of this. It's going to be really simple. So we're going to remind ourselves that the moment generating function is defined as the expected value of e to the power of t x. Okay, that is the moment generating function m sub x of t. And in this case, because this is a discrete random variable, it's going to be the sum over the sample space of our Rademacher distribution, and it's just going to be e to the power of t x times the probability that x is equal to little x. Now again, the sample space is just -1 and 1, and that is it. So we can very simply kind of work out what this is going to be. So it's just going to be, let's imagine when x is the number -1, it's going to be e to the power of minus t times a half, plus, and now this is when x is the number 1, it's going to be e to the power of t times a half, like that. And of course, we can simplify this to write it as e to the t plus e to the minus t, all divided by 2. And this is commonly known as the function cosh, or hyperbolic cos, or cosine of t. Okay, so what we have is if x has a Rademacher random distribution, then the moment generating function is actually just cosh of t. And of course, we can see that because cosh of t is a function that is defined absolutely everywhere, and the sum, there's no convergence problems or anything because it's a finite sample space, we can see that the domain of this is that t can just be any real number that we want whatsoever. And that's all there is to it. So as always, thank you for watching. If you enjoyed the video, like and subscribe, and I'll see you in the next one. Cheers.